Hi. The next rule we're going to discuss is called inverse function rule, and it relates, of course, to the inverse function that we were discussing in our initial classes. So, let's first start maybe by repeating a little bit what is an inverse function, and then we can move on to the differentiation rule for this function. Okay, so look, given the function y equals f of x, we get that x equals to f to the power -1 of y is what we're going to call inverse function. Okay, so look, even by looking at this, we see what we need to do. Look, f is going to be a sum formula here, right? If we solve this equation for x, we're going to express x in terms of y, and now we will have a new function where x is a function of y. But this is not always possible, right? So sometimes we cannot find uniquely defined x, and this is a big problem. Why? Look, for example, even with a quadratic function, we will always have two solutions. And it's not enough for us to be able to find x, but this x must still conform to the definition of the function. And look, what was definition of the function telling us? Definition of the function is telling us that for every x, we must have uniquely defined value y. Which of course means that for two x's, we can have the same value y, but what we cannot have is, for example, to have two possible y values for one x. And look, with some quadratic function, could obtain a result like this, right? And in these cases, we see that for given x, we have different values of y. This is no longer a function. So, before we actually proceed with solving this function for x, we need to make sure that as a result, we're not going to get an expression that is not a function. So, the condition that will actually allow us to do it is that f of x must be strictly monotonic. Okay, what do I mean by strictly monotonic? Okay, now let's use what we learned in logics, and let's use this symbol. What does it mean? For every, right? So for every, so we've got if for every x1 lower than x2, we have f of x1 is lower than f of x2. What does this mean? Look, it means that as x is getting bigger and bigger and bigger, value of the function is getting bigger and bigger and bigger. We call this a function that possesses this property. We call this function that possesses this property strictly increasing. Right? So this would be a function, for example, linear function, that always with higher x, we have associated higher y. But this function doesn't need to be it doesn't need to be a straight line, even if it moves like that, but it never falls, so it just drops in the rate at which it increases, we are still having strictly increasing function. Okay, then we can also write that if for every x1 lower than x2, f of x1 is bigger than f of x2, we call this type of function strictly decreasing. Now, look, how would this type of function look? Look, again, we could start with downward sloping linear function. The bigger the x, the lower the y. Or again, it could be some wavy shape, as long as it's always decreasing, just at a varying rate. Okay, so knowing this, we can define what means strictly monotonic. A function that is strictly monotonic is a function that is either strictly increasing or strictly decreasing. Now, if this condition is met, so if f of x is either strictly increasing or strictly decreasing, we can always find an inverse function. Okay, now let's go maybe to an example. Okay, let's just say that y is equal to 5x plus 25. Okay, look, this is a linear function. It has a positive coefficient, so we know that it's going to be strictly increasing, and by consequence, it's going to be strictly monotonic. Yeah, so now let's draw this function. I'm hoping I'm going to do it properly because now a lot depends on it. Okay, now first we see that if y is equal to, if x is equal to 0, y is equal to 25, and we see also that if y is equal to 0, then x is equal to negative 5, right? So it's gonna go like somewhere here. Okay, and I hope you remember this. If this is 0, here we get negative 5x. When we divide by negative 5x, we get negative 5. Okay, and look, if I'm gonna, okay, I need to do it a little better because I want the graph to actually see how the inverse function works. Okay, so look, this is our function. Now, if I want to find inverse function for this case, then what do I need to do? Well, I need to solve this for x. Okay, how am I going to go about it? Well, first, maybe let's move this to the other hand side of the equation. So we've got that 5x is equal to y minus 25. Okay, now we see that if I'm going to solve this, if I want to solve this, I need to divide both sides by x. And I'm getting that x is equal to 1 over 5y minus 5. Okay, now, what do I need to do next? Look, if I actually would like to put this function, this is already an inverse function, right? Because if this is y equals f of x, right? Then this function over here is x equals to the power negative 1 of y. Okay, look, I'm going to put it on the graph. So before I'm going to do it, I'm going to do a very simple trick. So everything makes sense to me. Over here, I'm going to put y. And over here, I'm going to put x. Because look, when we are dealing with some function, here we have arguments, and we like to have arguments on the horizontal axis, and here we have values, so we like to have values on the vertical axis. Okay. So, what do we get in this context? Look. Remember, now, like okay, y is over here, x is over here. So, first, if y is 0, x is negative 5. Okay, so here is our new x-axis. So we will have negative 5 somewhere over here. And now, if x is 0, okay, let's solve this so you can see it. It's 1 over 5, y equals negative 5. And look, again, if I move this to the other hand side, I'm getting that y is equal to 25. So let me put this more or less 25 over here. Now, I'm going to draw this function. Hopefully, I'm not going to mess it up too much. Okay. Okay, I know this is not perfect, but of course we are imagining that this is a straight line. And let's notice a very simple thing. There is a relationship between the two, which we should see right away. Look, here is negative 5, here is negative 5. Here is 25, here is 25. So those two are some sort of mirror reflections, but with respect to what? Well, with respect to 45 degrees line going through the origin. So this is the line where y equals x, right? Or from our different perspective, x equals y. In this case, it really doesn't matter. Okay, so now we've established relationship between these two functions. We see that they are mirror reflections with respect to this line. Okay, but as you might say, of course, this is always very, very easy in case of linear function. Let's try something different. Let's try function y equals x squared. Look, if we've got y equals x squared, situation becomes problematic right away. Why? Because this function is definitely not strictly monotonic, right? If I have y equals x squared, then I know that the graph of it is a parabola, and it's going to look like this. So we see that over here it is decreasing. Over here it is increasing. And look, if I would get a mirror reflection of this function with respect to 45 degrees line, or maybe I should do it, okay, give me a second, I should do it a little steeper, it's gonna look better. Look, what would happen? Okay, this part, let's start with this. This part should be reflected over here. So we should have mirror reflection, and it would look like this. Okay, which doesn't look that bad, right? But what about the other part? Okay, look, now I would have to draw a function that looks like this. You see? Because this is a mirror reflection, so all those distances, like this distance and this distance, should be equal. So we see what is happening. Now, this is no longer a function. Why this is no longer a function? Because look, if I'm going to take a line and I'm going to draw over here, what do I see? That for x0, we have two possible values of y. Over here, we've got some, let's call it y1, and over here we've got some y2. So this is no longer a function. And of course, if we want to find an inverse function, we need to make sure that it is a function. So, what can we do? Well, the trick to it here is fairly easy. We need to just restrict x's to be bigger or equal to 0. Look, which means that now, if I'm going to draw this, this function is going to start at this point and gonna go like that. Here we've got x, here we've got y. Okay, so now let's move on. This, of course, is our y equals f of x. Now, let's find x equals f to the power -1 of y. So, again, this is not very complicated because we restricted x's to positive values. So look, what I can do in this case is simply take both sides of this equation to the power 1 over 2. So I'm taking a square root out of both sides, right? So I'm getting that x, here those are multiplying, we've got x to the power of 1, equals y to the power 1 over 2, or simply y square root of y. Okay, so now, if I want to draw this, I'm going to use the same trick as before. So, I'm going to put y over here, and I'm going to put x over here, right? So, how does this function look like? Well, this function looks like that, which of course shouldn't be surprising because as you can see, this is what we got over here simply by using our mirror, and our mirror is the 45 degrees line. So x equals y or y equals x. In this case, normally we write y equals x. In this case, we are permitted to do any any way we want. Okay, so now we know basically how does it work. So here is our function y equals f of x, and here is a function x equals f to the power -1 of y. The same as over here. Okay, we will get to one more case. Associated with inverse functional. I just want to tell you one thing before, because there's one thing interesting over here. Look, if I restrict values of x to be bigger than 0, then look, this function has two common points. One is at 0, because we know, of course, that x 0 to the power of 2 is 0. Y to the square root of 0 is 0. And then we've got again point like this at 1. Why? Because we know that x 1 to the power of 2 is 1, and square root out of 1 is 1, right? But the interesting you're going to learn in the next couple of classes that we can actually find out that those two functions are dividing this area into three parts, right? This part, and this part. And look, the size of this area you see over here is 1 over 3, and it's equal to the size of this area, which is also equal to 1 over 3, which means that it is equal to the size of this area, which is equal to 1 over 3. We're going to prove it a little bit later using integrals, but for now, let's go back to inverse function, and now let's derive inverse function rule. And look, we're going to do it again using Leibniz notation of derivatives because it makes everything way easier. Okay, look, we said that before that derivative dy dx can be interpreted as a ratio of two differentials, dy to dx. And this is something we're going to take advantage of this time as well. Look. So what we're going to do over here, look, again, I'm going to start with the same thing I've been telling you all over. So that dy dx is equal to dy dx. And of course, this must be true because we have the same thing on both sides of the equation. And now look, what I'm going to do is I'm going to take both sides of the equation to the power -1. Let's remind ourselves, just to be sure, what does it mean? Look, if you have 2 to the power -1, well, this is easy. This is just 1 over 2, right? How did we do it? We took 1, we divided it by the number we have over here, right? Then, what about if we have 1 over 2 to the power -1? How much is that? Well, let's use the same trick we used previously. It's going to be 1 divided by 1 over 2, but this is the same as 1 multiplied, when we divide, we multiply by the reciprocal, 2 over 1, which is 2. Okay, makes perfect sense. Okay, so how about if we have expression like 3 over 4 to the power -1? Okay, let's use the same rule. Look, we can write it in two different forms. How? Look, first, I can simply take this as 1 over 3 over 4. Right? Right. Now, there is a second possibility. Okay, let's call this possibility the green possibility. And let's move on to what we can do next. Look, then I can just get 1, multiply it by reciprocal, so 4 over 3, and I'm going to get 4 over 3. And let's call this blue possibility. Okay, so look, from what we have established over here is that when I take a number to a negative power, I can use either blue possibility or green possibility because they are the same. And look, this is exactly what I'm going to do over here. On the left-hand side, I want to have the blue possibility. And on the right-hand side, I want to have green possibility. What does what is this giving? Look, if I'm going to have a blue possibility, what do I need to do? I need to reverse denominator, put in numerator, numerator in denominator. So I get a different derivative. Derivative dx dy. Now, but on the right hand side, I want to use a green possibility. So I'm going to do it as 1 divided by dy dx. And this, what you see over here, is the inverse function rule. Not very complicated to get it, once we know how to use -1 power. Okay, and look, knowing the inverse function rule, as long as the inverse function exists, we can calculate the derivative of the inverse function. Of course, look, sometimes it is sometimes we need to restrict the domain like we did with the quadratic function, but this is why let's just say we're going to use an example with the linear function. Okay, so look, let's just say that we've got a function y equals 3x plus 2. Now look, and I can calculate easily dy dx, right? It's just 3. Like, nothing problematic over here. But look, what if I don't want to have derivative dy dx? What if I want to have derivative dx dy? Look, there are two possibilities of going about it. First thing I could do, which is way easier, is to use inverse function rule. Because by inverse function rule, I know that this is 1 over dy dx, 1 over 3. And it is done. Of course, there is a longer possibility. We can solve this for x. So we're going to get that 3x is equal to y minus 2. So x equals 1 over 3, y minus 2 over 3. And then we get, for this function, the dy dx is equal to 1 over 3, which of course is the same result. Okay, now I hope you can see that using this rule is easier. So every time we can actually find inverse function, so the condition of strict monotonicity is monotonicity, very hard word, is fulfilled, we can use this rule because it's gonna make our life easier. Okay. Now, when we know the inverse function rule, let's remind ourselves one additional inverse function that we've been using. Okay, we said that a function e to the power of x has an inverse function. Look, how does y equals e to the power of x looks like? Well, we said, we've established it a long time ago that this function look like this. Now, is this function monotonic? Of course. Look, it's getting here. If we would go to negative infinity here, it would be getting smaller and smaller and getting closer and closer to 0. Right? So it has a limit at 0, negative infinity, in other words. But look, if we go like this, we see that it's always increasing and it never stops. So we can find x out of this function using we can solve this for x and we should obtain an inverse function. How do we do it? Well, we use the properties of logarithms and I calculate natural logarithm of both sides. So I get that this is ln y times, equals e equals natural logarithm of e to the power of x. But knowing the properties of logarithms, I can take this x up front and I know that ln e answers me a question to which power I should take e to get e. So this is equal to 1. So, in other words, we get that x equals ln y is an inverse function for y equals e to the power of x. So look, now let me just replace x by y and y by x, and look, again we see that those two functions are inverses of one another. Look, I hope you remember that ln x, y equals ln x looks like, like this. Yeah, they are definitely mirror reflections with respect to y equals x. So 45 degrees line. Okay, now let me just remind you one more thing, that of course we could do the same thing starting from y equals ln x. Now, the case here is a little bit more complicated because instead of logarithmizing both sides, we need to take anti-log, which means we are getting e to the power of y equals e to the power of ln x. But look, what do we have over here? Logarithm is answering me a question here. To which power I need to take e in order to get x? I'm taking e to this power. So this is x. And we get that this is x equals e to the power of y. Or, again, if I change the names, y equals to power e to the power of x. Okay, so after this example, I hope you can guess what we're gonna do next. And of course, what we're gonna do next is logarithmic rule and exponential rule. And actually, what we're gonna do is we're gonna establish logarithmic rule first. We're gonna prove it, and then using the property that those two functions are inverse functions of one another, we're going to use inverse function rule to obtain exponential rule. Okay, thank you for your attention and see you in the next video.